Hello and welcome to our guest speaker, Deb Gajic. She is going to explain all you need to know about research methods in psychology. This episode, Deb is giving us information about research methods and the maths element in the exam and what you need to know for data management. The host asking the questions is Blakemore.
We're looking at research methods. So why would you say research methods is so important in psychology?
Because research methods really are the foundation of psychology. Psychology is a science, and we can't have theories without evidence. So, in order to get that evidence, we've got to carry out our research. We can't just have an educated guess or a hunch. We've got to be able to say our evidence shows, or we've observed, or we've got to be able to substantiate our claims. For students, it's really important because at A level, 25 to 30% of the assessment is research methods. So if you've got a good understanding of research methods, then you're a third of the way there to passing your course, really. And it's also really, really useful for evaluation. So when you're writing extended writing answers, if you can evaluate the research method, that's a really good starting point to get your evaluation points in.
So why do you think students find data analysis so tricky?
Fear of maths. Fear of maths is a really big thing. And I think it's a cultural thing. If people can't read and write, they actually go to great lengths to hide it. They don't go, oh, I can't read and write. They pretend or they find strategies. But it seems to be acceptable to say, I can't do maths. And I always wonder where that comes from because very young children in primary schools, are usually very proud that they can count. They don't think I can't do maths. It comes later on. Um, so I think that's something we need to address with our students, that a lot of the time it is lack of confidence and there's a fear of getting things wrong. So
Mm.
it's about creating that classroom culture where it doesn't matter if you make a mistake. We all make mistakes, we're all human. I also think it's a good idea to point out that the calculations that students need to do, especially in exams, are usually really simple and they are allowed a calculator. So it's not that difficult. I've found that because I'm not a maths specialist, I'm what I'd call an enthusiastic amateur when it comes to maths. I do love it, but I'm certainly not a maths teacher. A lot of my students have said that they've enjoyed the way I've taught it to them because I've taught it in a non-mathsy way. I
Mm.
think it would probably make maths teachers wince, but it's a way I put it in sort of a simple terminology that they understand. I
Yeah,
also
I
think
find
it's
that. Sorry, I was going to say, I find that when you found it difficult to work out how to do things yourself, you find it easier to teach somebody.
definitely, definitely. I can remember finding um, percentages really hard when I was a child. I really didn't get to grips with it. And I think because I struggled with it and had to really think about it, I can now teach it in a way that makes more sense. I always advise my students as well to do the eyeball test, face validity. What sort of answer would you expect? So if you're working out, for example, a really simple example, 50% of 200, if you get an answer of 150, common sense tells you that that can't be right. So then you go back to the drawing board. So just using that, face validity, that eyeball test, does my answer look about right? I remember years and years ago when I was doing my master's, I was doing a stats exam and the exam involved a little bit of number crunching. And one of the things we had to do was work out the weight of a lab rat because we were given the dosage of drugs they'd been given. And we got how many, what the dose was per 100 grams. And I can remember working it out, and my rat came out at 4,500 grams, so 4.5 kilos. And I'm thinking, that is a damn big rat.
Big rat.
So I tried it again and got the same answer again. And in the end, I just thought, I'll just have to put 4.5 kilos. When I came out of the exam, everyone had had the same problem. So it was a problem with the exam question, not working it out. But I was annoyed because I spent so much time thinking, I got the naught in the wrong place, because
Mm.
surely that would be about 450 grams, not 4,500 grams. So sometimes the exam questions can be tricky, but I digress.
Yeah.
One of the things I'd always say to students is ask for help. Don't sit in silence. There's probably half of your class who are also thinking, I don't know how to do this. And I would say to teachers, don't assume just because students have got a grade 7 in maths that they know everything, because often they don't.
Mm.
If your school offers core maths as an option, it's a really good idea to try and encourage your students to take that as well. Not only does it count towards their UCAS offers, but it's really helpful for any maths in their other A levels. But I think, yeah, it's students find it tricky, but it's about building up your confidence. So the more you practice, the more exam questions you do that will have maths involved, the better you'll get.
Good advice. So what do you think, sorry, what is the difference between descriptive and inferential statistics?
Descriptive statistics do exactly what they say. They describe or summarize the results. So things that students will be familiar with are mean, median, and mode. It doesn't help that we call them measures of central tendency in A level when they were called averages at GCSE.
Yeah.
But actually, I've heard that the new reform of the curriculum is going to look at standardizing language across all subjects and all levels, which would be wonderful.
Good.
Things like graphs, tables, all of those, standard deviation, range, they all are the first step in our data analysis. They enable us to identify patterns. And again, the eyeball test, what does it look like? You know, if our mean for group one's really high and group B it's really small, what's that telling us? So descriptive statistics are really important to tell the story of the data. And I always think that's the first level of analysis. What does it look like? What do you think your results are telling you? Now, the issue with descriptive statistics, of course, is we can't come to any conclusion. We can only find patterns. So, in order to come to a conclusion, that's where we need inferential statistics, which, as the name suggests, allow us to infer conclusions from our data. Now, I think students get a bit scared of these because they look tricky, but actually, you know, once you get to university, you use stats packages to work them out. It's not that difficult. So, inferential statistics are all about finding out whether our results actually support our original hypotheses. Did we find evidence to support what we were saying in the first place? So, sorts of inferential statistics that students will probably look at will be mainly what we call non-parametric, so Spearman's Row, chi-square, sign test, Mann-Whitney Youth test, Wilcoxon, etc. But for most of the specs, you only need to know really when you would use them, which test you would use when, and maybe know how to calculate one of them. So again, it's not as scary as it looks at first glance.
Great. So probability, why is it so important?
Probability, again, is something that students will have done, you know, right from probably year 7. And we all know the idea, don't we? If we flip a coin, the probability of it hitting heads is 50%, or, you know, 1 in 2, 0.5 is a decimal because we know it's got a 50-50 chance. If we make that a bit more complicated, if we flip 2 coins, and we want to know the probability of them both landing heads, then that would be 1 in 4, because there's 4 possible outcomes. There's 2 heads, 2 tails, tail and a head, or a head and a tail. So we've then got 25%, or 1 in 4. So probability in itself isn't that difficult a concept. What we need to get our heads around, I think, is that nothing in life, except that we're all going to die, is 100% certain.
This
Morbid, that one, isn't it? But it is true. You know, nothing's
taxes.
100%. It might be 99.9%. You know, I might say the probability of it going to rain in the next 7 days is probably 99.9999999% because we live in England. Um, but nothing's ever 100%. Things can change. So when we have a hypothesis, we want to know how many of our results would we accept as being due to chance. We're accepting it's never going to go 100% the way we predicted, but what would be a good level? Now, in psychology, we tend to use the 5% level, or the 0.05 or 1 in 20. And what that means is we want to be 95% confident that our results were not due to chance. So if 1 in 20 is a bit of a rogue result, we can still say we found evidence to support our original hypotheses. Now, the 5% level is fine in psychology. If we were testing a new drug, for example, if we were medical statisticians, we'd want a much stricter significance level, wouldn't we? The fact that 1 in 20 of our participants might drop dead from the drug that we designed wouldn't be good, would it? We might want we might want something like 1 in a million rather than 1 in 20. But we know even with drugs, people are allergic. You're never going to get a drug that's 100% safe. If ever you go to the chemist, you get your big list, don't you? That's like this of all the possible side effects you could have.
Okay, so why do we use the 5% level probability
We
in
use
psychology?
that because it represents that balance between making a type 1 and a type 2 error. So it's the balance between not being too strict and not being too lenient. I always think it's a bit like Goldilocks and the Three Bears. Not too big, not too small, but just right.
Okay, so you've just mentioned type 1 and type 2 error. What are they?
Oh, well, yeah, these strike fear into the hearts of students, don't they? As an undergraduate, I was always told it was better to make a type 2 error than a type 1 error, because a type 1 error is being lax, isn't it? It's being too lenient. So type 1 error is a false positive. So we reject the null hypotheses when actually the results could have been due to chance. So actually we needed to accept the null hypotheses. So that might be caused if we said used a 10% level. And the opposite of that is being too strict, a false negative, when we're expecting, say, only 1 in 100. So we accept the null hypotheses when we should have rejected it. I think type 1 and type 2 errors are something that students find difficult. Luckily, they don't ask too many questions on that. The ones I've seen have tended to be, why do we use the 5% significance level? And obviously because it represents a balance. And the other type of question has been, the researcher thinks they might have made a type 2 error because they use the 1% level. What should they do? Oh, well, they can use the 5% level. Or they might have made a type 1 error. What should they do? Well, use a higher level. So the questions aren't too difficult. I think it's just the concepts that are quite difficult.
So students will need to know the difference between type 1 and type 2.
They will, yes.
Okay, so hypothesis testing, what is it?
I think this is sometimes where students find inferential testing difficult because they don't realise what they are doing with an inferential test. We always have two hypotheses. We have our prediction, what we expect to happen, and we have our null hypotheses that any change is due to chance. So what we're doing with our inferential testing is we are testing that hypothesis. Have we found enough evidence? So what we were talking about before. So did 95% of our results go the way we expected? So, I mean, for example, if we were testing, say, context-dependent memory, and we were looking at it, and our mean scores told us that when they were in the same room, they remembered 18 words, and when they were in a different room, they remembered 12. Well, that might start to tell us that it looks as though our results might be significant because we're looking at our descriptive statistics. But in order to be sure, we need to carry out that inferential test to see, and we always talk in terms of the null hypotheses, should we reject or accept the null hypotheses, which of course in practice means we're also talking about accepting or rejecting our alternate hypotheses as well.
Okay, good. So why do we need to operationalize variables in hypothesis?
Again, a common problem with hypotheses writing is not being precise enough. If you don't say exactly what you're manipulating, your independent variable, and exactly what you're measuring, your dependent variable, then you can't be sure that there has been a change. So if you're just being really vague, like females will have better memory than males, well, what does that mean? What do we mean by memory? How can we test that? So we need to be very clear and state our variables in a measurable form. So commonly, we're doing memory, we'd say, females will remember more words from a list of 20 common words than males will. So we need to say exactly what it is so that we can get a valid measurement. We also need to think about our IV as well. Obviously, the example I've just given us, gender's quite straightforward, male or female. But if I wanted to say something like time of day will affect memory, I've got to operationalize time of day as well. So if I said morning or afternoon, even that's not precise enough. I might say 9 o'clock in the morning and 6 o'clock in the afternoon, because we need to be really precise. And it's all about this idea, isn't it, of psychology as a science, being precise, having measurable, operationalized variables so we can be objective, so we can measure what we set out to measure. So it's all about really reliability and validity.
It's great. So what's the difference between a directional and a non-directional hypothesis?
We refer to these as one or two-tailed when it comes to inferential testing, but it's still the same. If you think about directional, one direction, that's the group. If we think about directional or one-tailed, we're going in one way, aren't we?
Mm.
So we'd say things like, for example, alcohol will increase reaction times because we've said exactly what we expect to happen. If it's non-directional, it's two-tailed, so it could go either way. So then we're talking about alcohol will affect reaction times. We haven't said whether reaction times will increase or decrease. So a non-directional one is much less specific. It's saying there'll be a change, but I'm not really sure what the change will be. Whereas directional is saying it will go up, it will go down, it will increase, it will decrease, it will be bigger, it will be smaller, etc. And if we'd got a correlation, if it was directional, we'd say there'll be a positive or a negative correlation. And if it was non-directional, we'd just say there'll be a correlation or a relationship. Now, when we come to write hypotheses, especially in exams, there's a key thing we need to look at to decide whether we write a directional or a non-directional hypothesis. And that is simply whether there's been any previous research. Because if there's been previous research, it's probably told us what the direction of influence was. If there hasn't, we don't really know. So we have to use a non-directional one.
Right, that's a great tip. So any tips to help remember which test to use and when?
Well, yes, this is one of the things that students find hard. They will have all seen the little table and they need to memorize that table. Now, when you're choosing a test, there's 3 questions you ask yourself. First of all, is it a test of difference or relationship? Then we need to know what design to use. Is it a correlation, independent measures, repeated measures, matched pairs? And finally, what's the level of data? Is it nominal, ordinal, interval, or ratio? So the first thing that candidates need to do is make sure that they understand what those things are. What are the designs? What are the levels of data? What is a test of difference? What is a test of relationship? Once they've done that, then the key then is really to draw that table out as many times as you can. I would also suggest putting it on a poster on your bedroom wall. One of the little things that I used to do with my students is print them out blank grids with just the headings of, test of difference, test of relationship. And then with post-it notes, stick in the gaps the correct test. And it's one of those things you can reuse to test yourself. And again, looking at as many past questions, this is a really common exam question. Some people make up little mnemonics as well to help them remember it, little rhymes. I've never found that works for me, but that's just me personally. I prefer to draw things out and keep looking at it. But if mnemonics work, then for lots of people they do. And I think it's interesting as an examiner, I often see on the front of exam papers that the first thing the students done when they've got in the exam room is draw that table on the front of their booklet. It's like, I've got it in my head, I'm drawing it now so that when I come to the question, I know it.
Excellent. So what are critical value tables?
Okay, so once we've done our calculation and we've got our calculated value, we've got a number, we need to know what that number means. Is the result significant or not? And that's when we consult critical value tables. Again, there's things we need to know to be able to use critical value tables. We need to know whether it was a one-tailed directional or two-tailed non-directional hypothesis in the beginning. We need to know the significance level, which will normally be 0.05. And we need to know for some of the tests what we call the N value, which is simply the number of participants. If we're using chi-square, t-test or Pearson's, though, we need to know the degrees of freedom. But they'll always tell you how to calculate those. I won't go into that now, but obviously that could be the point of another blog, couldn't it?
It could, yeah.
So what we then do is we compare our calculated value with the critical value. Now, it will tell you on the tables whether your calculated value has to be more than or less than the critical value, which is another confusing thing because of the way the tests work. You'd hope they'd all be the same, but they're not. It's some maths thing. So some have to be more, some have to be less. The easy way to remember it is any test that has an R in the name, then the calculated value has to be more than the critical value. So Spearman's, chi-square. If it doesn't have an R, sign test, Wilcoxon, Mann-Whitney, it has to be less than. And then we just look it up and then we can see whether or not we can accept or reject our null hypotheses. Does it meet those criteria? One thing that I will point out, because this sometimes does lead to confusion, when you calculate Spearman's rho and you get a correlation coefficient, the plus or the minus at the front of that number doesn't have a numerical value. It's simply telling you whether it's a negative or positive correlation. And I only mention that because in Spearman's, the calculated value has to be more than the critical value. And I've sometimes had students say, well, my answer's minus 0.76. Surely that's less than 0.6. No, it's not, because we ignore the minus. So that's just one thing to think about.
Excellent. So practice is the key, yeah?
Practice is definitely the key. Yeah. As many past paper questions as you can do. And if you're unsure, ask your teacher. Don't suffer in silence. Make sure, and the earlier you get those misunderstandings cleared up, the better, really.
Yeah, that's fantastic. Thank you very much for that. Thank you very much, Deb, for your advice on this part of the exam. We look forward to hearing more from you about research methods in psychology A-level.